Thank you for watching our video. I'm Naoki Akai from Nagoya University, Japan. Our presentation title is Bayesian Filtering Fusion of Optimization-Based Molecular Visual Localization and Autonomous Quadcopter Navigation. First, I would like to share with you what this work does. In this work, we present a fusion method of optimization-based visual localization with Bayesian filter. To achieve this, we need to estimate uncertainty of visual localization result because the optimization-based localization does not output uncertainty. Then, we fuse the visual localization result with inertia-based localization, that is odometry. Owing to the uncertainty estimation, we can apply Kalman filter for the fusion. By using Bayesian filtering fusion, we can estimate whether visual localization is confidential or not. Because we can know confidence of the estimate, we can appropriately use the visual localization result for the fusion and can estimate smooth trajectory. Let me start the introduction of our research. Recently, many valuable open source software for visual localization are available. ORB SRAM 2 is very famous and it enables to achieve accurate camera tracking. In ORB SRAM 2, bundle adjustment, that is the optimization-based key point matching method, is used. In the bundle adjustment, pairs of the key points are determined and the distances between the pairs are minimized. ORB SRAM 2 is very nice software. However, it still has a problem because ORB SRAM 2 uses the bundle adjustments. It estimates weak to measurement noises. ORB SRAM 2 might fail if incorrect pairs are determined due to the measurement noises. In addition, estimated trajectory by ORB SRAM 2 is jarred, since it is the optimization-based method. Our work enables to estimate smooth trajectory as indicated by the red line in the bottom right figure. I would like to introduce Bayesian filtering here. Bayesian filter estimates the posterior distribution using prior and right lift distributions. In this work, we use inertia-based and camera-based localizations. The estimates by the inertia-based and camera-based localizations correspond to prior and right lift distributions, respectively. Let me show you the graphical abstracts. Let's say we have a drone pose with uncertainty. The drone moves and pose uncertainty increases. This increases the distribution is deferred to prior. Then we can have sensor measurement from an external sensor like a camera, and the drone pose is estimated. Here, we do not directly use the external sensor-based localization results. Instead, we estimate the distribution based on the external sensor-based localization results. This distribution is called as the right lift distribution. Finally, the prior and right lift distributions are fused, and the posterior distribution is estimated. This process is iteratively performed, and the drone pose can be continuously estimated. However, we have a problem. In order to apply Bayesian filter, we need to estimate the right lift distribution. That is, we need to determine uncertainty of the camera-based localization results. However, the optimization-based localization does not output the uncertainty. To overcome the problem, we apply a method presented by Bengston and Barrett presented in ILOS 2001. The method estimates the uncertainty of the optimization-based localization using Hessian matrix. The Hessian is used in the Newton method. They suggested that the inverse of Hessian is similar to the real uncertainty. We apply the method to fuse ORB SRAM 2 estimate with inertia-based localization. This is a system overview of the presented localization method. We use ORB SRAM 2 as the visual localization method. In ORB SRAM 2, G2O is used for the optimization. The uncertainty estimator receives the visual localization result and determines the uncertainty. This detail is explained later. Then, the fuser receives the localization results from the inertia-based localization and the uncertainty estimator and outputs the pose. This fuser is implemented using a Kalman filter. Let me explain detail of the uncertainty estimator. This equation is solved in detail for performing optimization. In this equation, we have three elements: Hessian matrix, gradient, and increment. Indices P and L represent information regarding pros and random respectively. In this work, we focus on localization, hence the update equation regarding the pros is important. To get the increment for the update in optimization, this equation is solved. Here, the matrix before delta x has the property of Hessian matrix. We denote this matrix as H bar, and the uncertainty of the orbit RAM 2 estimate, that is covariance matrix, is determined using the inverse of Hessian, whereas sigma is the scale factor, and that is determined experimentally. Let me show you experimental results from here. We first compare the performance of uncertainty estimation and the different measurement conditions. The green points depicted in the top figures are the key points extracted by ORB from 2. The bottom figures show ellipses calculated from the covariance matrix, that is uncertainty for the ORB round 2 estimate. In the left case, match key points are observed. In the middle case, we made occlusion. In the right case, match key points are not observed. Compared to the uncertainty estimation results, we can say that the uncertainty increases if the measurement condition is bad. From the results, we confirm that the uncertainty appropriately changes according to the measurement conditions. We also implemented kernel filter fusion for quadcopter navigation. This is a pursuit algorithm for kernel filter. In the first line, the motion model of a quadcopter is used to predict X bar. All T and X or B shown in the third and fourth lines are estimated by ORB round 2 and its uncertainty. Based on this fusion, we determine the uncertainty over the posterior. In the left figure, estimated trajectory by ORB round 2 and presented method are shown. The trajectory estimated by the presented method is indicated by the red. We can confirm that the presented method can estimate smooth trajectory more than ORB round 2. In the right figure, we show the estimated trajectory with curvature. If the trajectory curve close to the break, we can say that the estimated trajectory is smooth. We also conducted localization experiment with constant matrix case. In this case, the presented method, in this case, the presented covariance determination method is not used, and the covariance is constantly determined. The curvature is the smallest when the constant covariance matrix is used. However, this is another problem. We calculated the differences of the estimates by the kernel filter with ORB round 2 in each element. If the differences are zero, the outputs by kernel filter are the completely same to the estimate by ORB round 2. The differences between ORB round 2 and the presented method are indicated by the red. The blue indicates the differences of the constant covariance matrix-based fusion. The differences of the present method are smaller than that of the constant covariance matrix-based one. Basically, there is a trade-off relationship between smoothness and the post-tracking accuracy. From these results, we confirmed that the presented method can be balancing this trade-off relationship. Finally, we conducted autonomous flight experiment with a quadcopter. In this experiment, we cannot implement better path tracking methods. Consequently, the drone deviated from the target path depicted in the green line. However, our method can continuously and smoothly estimate the drone path. The estimated trajectory is indicated by the purple line. As a result, autonomous navigation can be achieved. We would like to announce that the software used in this work is publicly available. Let me conclude this work. We presented the fusion method of optimization-based visual localization with inertia-based localization using Kalman filter. To achieve the fusion, we presented the uncertainty estimation method for the visual localization results. To estimate the uncertainty, Hessian matrix, which is used in the optimization process, is utilized. We first tested uncertainty estimation performance under different measurement conditions and confirmed that the uncertainty appropriately changes according to the measurement conditions. By using the fusion, we achieved the smooth trajectory estimation while maintaining the pulse tracking accuracy. Our future work is to perform quantitative evaluation for the uncertainty estimation. In addition, implementing an accurate path tracking method for the drone is also our future work. Thank you for watching our video.